Hello everybody, welcome to GIS lesson today, and I'm sure by now you also would have started loving the subject. I am Dr. Seema Mehra Parihar, who's been teaching GIS remote sensing for last 30 years now. I've had my share of education from Delhi School of Economics, my PhD. My postdoc is from ITC Netherlands, and even I've had my share of learning from Indian Institute of Remote Sensing, Dehradun. So now let's start working and let's start understanding about the data storage and compaction in geographic information system. It's a part of remote sensing and GIS course. Today we are going to learn following things. Number one, relevance of storage, relevance of compaction techniques, the need in GIS about the storage techniques. We are also going to learn about the four ways in which the raster GIS, the data can be stored. And in addition, we are also going to learn about the vector GIS storage capabilities. That is, we are going to talk about spaghetti and topological model. Let's begin the journey. In your previous chapter on data models, you have understood the relevance and importance of raster and vector. And by now, you also all know that what is raster and what is vector. What we are going to talk about today is that this object based data, spatial database which exists, it has to be stored. Your images, your remote sensing data, all these things are there in layers and they all have to be stored, as it's also written in the Parihar's lecture. On the other hand, when the spatial database is structured in the field based model, the basic spatial units are different forms of tessellation, and these are termed as raster data model, and both of them have slightly different ways of getting stored. And the storage and manipulation of various location based data sets and related attribute information in both the model is very relevant and consequently have received a lot of attention. Obviously, because ultimately we have to retrieve data, and how will we retrieve? We'll only retrieve if we have stored it correctly. And we've also realized by now that every data to be considered in GIS environment is to be treated as unique, because computer only works what we say to the computer. We all know by now that it's a garbage in and garbage out, and so is the case out here. We all have to see also that the data is stored and we do not have redundant data stored, because at the moment we have redundant data storage, it will occupy more space in the computer. And to understand this complexity and related concerns, this chapter is divided into two sections. One related to data compaction techniques in raster GIS, and second related to data storage techniques in, guess what? Yes, you guessed it right, vector GIS. And today we are going to talk about now data compaction techniques in raster GIS. Data compression techniques in raster GIS has different algorithms, and they reduce the size of the computer file but maintain all the information intact. And compression algorithms may be two, one lossless and another lossy. What is that? Lossless is where no information is lost, and lossy is where some information is lost. Lossy algorithm is generally applied to thematic data, but largely applied when image data is considered. Mostly they are applied to discrete raster data algorithms. So listeners, what are the two types of different this thing? Yes, you're right, lossless and lossy. In one, the information is lost. In another, just little information is missing. So consequently of learning this information, let's carry on learning forward. The data compression or the compaction in a grid-based raster GIS environment has been studied and researched upon by many. Many compaction techniques in raster GIS have been evolved in different years, and for our purpose, the techniques considered today are four. Number one, chain coding. Number two, run length coding, block coding, and quadtrees. So that means, what are the learnings? C, R, B, Q. What is C? Chain coding. R, run length coding. B, block coding. Q, quadtrees. Let's now learn one by one. The first one, chain coding. You all know what a chain is? Chain. Chain coding is largely undertaken as a clockwise coding method and is generally referred as Freeman chain coding. You understand that? Chain. And we are talking about raster. That means, what are we talking about? We are talking about clockwise movement in grids. So to begin with, from the following figure which you can see in your PPT, locate the cells required for storing the given entity. So we are going to count those and we are going to move forward in a grid wise, in a clockwise direction. So you move like this. And the moment we know it, it's an easy and simple technique, a very straightforward technique. In a chain coded representation of a map, using any starting point on the border of an object, the sequence of cardinal directions of the cells that make up the boundary of the objects are recorded systematically in a clockwise direction, and this is a clockwise direction. The polygon is defined in terms of unit cells measured in cardinal directions. That's what the way Freeman says, and we also know it. The steps are as follows. Number 1, identification of points by number ranging from 0 to 7. For example, east may be identified as 0, north as 1, west as 2, south as 3. You may select your own numbering system. Once a move in the direction of the line is made and recorded, the locational grid is recentered over a new location and the next move defined in the same way in the clockwise direction. The advantage of this chain coding is that it enables storing raster data, and above all, it is very useful for detection of sharp turns and area estimation. The shortfall is that there is a repetition of data, and do we want it? Of course not. We do not want it, because that will take a lot of space. So chain length coding we have learned. So just remember, the moment we talk about the chain length coding, we have to remember another C, clockwise. Let's now talk about run length code. Run length code is an improvement over the conventional chain code technique, and this is suitable to the personal computers with limited storage capacity. It stores a single value for a group of cells instead of storing the value for each individual cells. That means group of cells are stored. This method exploits the fact that many data sets have large homogeneous region. In this procedure, adjacent cells along a row that have the same value are treated as a group and termed as a run. Each row in the grid, 1 pixel width is examined in turn, and pixels having the same value, that is homogeneous pixels, are grouped together. It uses an ID method of grouping the pixels with similar or identical values. Say for example, I just want to tell you, say somebody is clicking a picture from above. What will happen? In case if it's an ocean, all the pixels around of that picture would be water. You may find also somewhere a little land. You may also find little trees somewhere. But generally, in an image, you may find a lot of homogeneous groupings. And this run length coding takes care of that. If it's water everywhere in an ocean, this picks up that water component as one group. So let's move forward and understand this little more. Locate the pixels which are with similar values, and that means water, trees and all that. And then second is position reference be noted. Then sequences of pixels with similar values are replaced in the memory by the positional reference to the first pixel in the grouping and by the number representing the number of pixels in the grouping, as so very clear in the picture. Now when we look at it, the figure which is there, you find that in the first row, what is it? 2, 9, 5, 6, 1, 7. Second row has 8, 6 numbers. Third row has 2, 9, 4, 6 and 2, 7 numbers. Fourth and last row has 1, 9, 1, 8, 1, 9, 2, 6, 2, 7, 1, 5. So these are the numbers which are there representing groups. One is representing number. Run length coding is common and rather simple method for compressing the raster data. The left number in row 2 in figure 2 depicts the number of cells in run, 8 in this case, and the right size of the cell is 6 in the case, and the value together is 8:6. Though a simple method, its major shortcoming in the words of the Wood is that the pixel groups are identified only in one coming in one direction, parallel to the x-axis. As a result, the nearby rows, that is those above below the current row, which may have the same values of the group, are represented separately. So what have we learned? We have learned by now two methods, chain and block, run length. Now let's learn about the block code. Block codes are a two-dimensional extension to the run length code. It assumes that the cells are recorded in the form of blocks of squares. Earlier, what was the case? Yes, recapitulate. Yes, it was one row and we noted the numbers. How many numbers representing one pixel value or a group of pixels. Now we are considering the blocks. Water, if water is covering 4 blocks, then that's one block. Trees or the vegetation is covering another say 9 blocks, then that's one. So that means we pick up the blocks. The method that uses is a square blocks to tile the area to be mapped, as Burrow said. This method has largely been applied in performing union and intersection of regions and for detecting properties such as elongation. The steps undertaken in giving block codes are locating as many large square blocks as possible in the given raster image. The codes be noted through the medial axis transformation, what we call MAT, from the square blocks, and the blocks are arranged in the hierarchical form. Note that. Figure 3 represents the block code method and is based on the Haywoods. According to the Hayward, a unit square represents one cell, whereas in 4 square blocks represent 2 into 2 cells, 9, 3 into 3, and so on. What did I say just now? I said 4 square block represents 2 into 2, 3 square, 9. The larger the square that may be fitted into a region, the more efficient the block coding becomes. Is it clear? And that's something which is there. So just tell me, I've just talked about the 4. The moment you have 4, what does it mean? 2 into 2 matrix. The moment you have 9, what does it mean? 3 into 3. And if it's 16, what does it mean? Yes, oh yes, you are very intelligent. 4 into 4 is 16. And that's something which is so very important. So now we are clear about the 3 techniques. Yes, which are those? Yes, the first started with C, second was R, and the third was B, CRB. Let's now come to the Q, that is quadtree. What is this? Tree you know it, and quad also you know. So the 4th raster compression method is quadtree method. It's a variable spatial resolution model, sometimes equated with hierarchical tessellation model. A quadtree is a term used to describe a hierarchical or tree-based data structure whose common property is that the structure is based on the principle of the recursive decomposition of space to represent both vector and raster data. It is similar to run length coding and are largely used while compressing area features. They generally represent raster data structures with variable spatial resolution, and this can be best understood in case if we look at the figure 4. Yes, variable spatial resolutions are noted, and each specific area feature has to be delineated, and with each feature which is there, or if of different size, they are coded and they are assigned the codes. And first to the larger raster cells, then fit into the one uniform area. Successively, smaller cells at each iterations are halved cell dimension until the smaller cell size is reached. And this is something which is so very clear if you look at the figure 4, which talks about the data compression in a quadtree method. And one of the advantage of this raster data model is that each cell can be subdivided into smaller cells of the same shape and orientation, and the quadtree model addresses both the resolution and the redundancy issue. So that means, what is the advantage? 2 R's we take care, resolution and redundancy. This method so that point in polygon searches also can be performed easily. So by now we have learned all, but let's just carry this a little forward. Burrow is of the view that the largest problem associated with the quadtree is that tree tessellation is not translation invariant. 2 regions of the same shape and size may have quite different quadtree, and I think so you understand that. So consequently, shape analysis and pattern recognition are not straightforward. Another disadvantage is that it is time consuming to create a quadtree data structure every time. The moment the shape changes, resolution changes, and so on and so forth. And this implies that a rebuilding of the entire quadtree is required just by a mere change in the original data set. I mean, you have to recreate it every time the moment it changes. Is it clear? So, dear friends, what have we learned by now? We have learned 4 data storage and compaction techniques of raster GIS. Close your eyes and just revisit them. Very good, wonderful. Now let's move to the second data model. One was raster, what was the other? Oh my God, everybody is answering correctly. Yes, it is vector storage. Let's now talk about data storage in vector data. We know by now that the vector data model represents anything from a simple number to a complex entity. This we learned in the previous lesson also. It is an object-based approach to the representation of the real world features and is best used to represent discrete objects. It is certainly straightforward when only simple polygon is represented. But with the introduction of a complex entity such as more than 2 polygons, the adjoining boundaries will cause duplication of adjacent line and so need more space in the computer. Moreover, there are also many matching problems that occur while overlapping 2 sets of some adjoining boundaries. To overcome this and the related problem, there are 2 models. Out here, the 2 models which we all have to remember are ST. S is spaghetti model. Oh my God, you all are feeling hungry? Yes, spaghetti model reminds of that. Topology model is the second one. Let's now take a journey to spaghetti model. And so, which are the 2 techniques of vector? ST, spaghetti, and second is topology. Let's now take a journey of learning of spaghetti model. Spaghetti model, what is it? It is a vector data that have been collected but not structured are said to be spaghetti data model. Like a plate of cooked spaghetti, you all must have eaten, with no ends connected and no intersections affecting the plate. It's the same way. It's also called a non-topological or geometric or path topological model. It was originally developed to organize, manipulate and store line data, generally used for the line data. And the spaghetti model enters each line separately through number 1, storing the starting node, 2, storing the end node, 3, storing the vertices to note the change in directional or path, and not storing, recognizing when the 2 lines meet or cross each other. And figure 5 out here clearly shows you the spaghetti model with 6 lines. So, generally it is a line storage, again where the end and the beginning is stored. As figure 5, if you see, it depicts that the spaghetti model records each of the 6 lines in the figure separately. What is to be noted is that the connections are not recognized and nor is the crossing over or meeting points of vertices. It looks like a map but without underlying structure. Graphical elements are stored and not the graphical entities. Understand this. Graphical elements are stored and not the graphical entities. Beginning point, end point. This is stored. The moment you cross, it is not stored. Right? The moment you have an overlap, it is not stored. That's something which is so important. And the spatial relations between the features are not retained, therefore. In other words, we can say it's a collection of points in line segments with no real connection. All the information necessary to draw a map is in a place, but is randomly organized, unlinked. This makes organization of the data easy, but makes it very difficult to use for analysis. The spaghetti model does not retain any specific relation. The positive aspect of the spaghetti model is that it's relatively efficient as method of cartographic display and used in computer assisted cartography, like CAD, AutoCAD and all that, where analysis is not the primary purpose. Primary purpose is the drawing, analysis is not. Analysis is important for GIS. So in CAD, what is important? What is used? We need graphical, we need all those maps, we need all those your building maps, we need all those land use maps. For that, spaghetti model is good enough because we are not looking for analysis. Following up this is the point dictionary model. What is this? Point dictionary model. Spaghetti model, point dictionary model. You'll say from where has it come? This is in between topological and spaghetti. So I have not said it's separate. This is a point dictionary model. A marginal improvement over the path topological model, that is the spaghetti model, is a point dictionary model. In this model, both the transformation between numerical coordinates and points is incorporated. That means numerical and the points are incorporated. All coordinate pairs are numbered sequentially. All coordinate pairs are stored in random access allocation. List of the point ID, the unique ID prepared as the address for accessing the appropriate coordinate, and each polygon is stored as a circular list of the points. Simple. If you look at the figure of the point dictionary model, it will become much more clear. Therefore, as depicted in this figure, you'll find that the storage requirement are slightly reduced as XY pairs are stored only once. However, each point ID is still stored twice for common boundaries. Though this model saved space in the system, but the adjacency problems still remain. Thus, the point ID values are first retrieved from the polygon list, which in turn are used to retrieve the respective coordinates. And that's again something which is so very important. That means though we are saving than the previous one, spaghetti, but again adjacency problem still exists. That means we are again getting redundant data. Okay, do we have any other method before we come to the topological model? Yes. Let's take ourselves to the second one, third one, or you can say 1A, B, and then second is the topological. Chain dictionary model. What is this chain dictionary model? Chain dictionary model is used to reduce and even overcome most of the time the adjacency problem, that is adjacent boundary problem. The retrieval of area features of polygon is a three-step procedure in the chain dictionary model. First is retrieval of polygon ID, second retrieval of point ID, and third retrieval of corresponding coordinates. And the figure or the diagram depicts that, the chain dictionary model, and becomes clear to that. That means we are retrieving all, and so this is better. So that means in case if we think of it, what we think of it? We think of it that the first we take spaghetti, and then we come to the second one, and then we come to the third one. But the ones which we are talking about is now topology model, which is also a branch of mathematics, topology. Yes, topology. So what are the two vector GIS storage models? S, spaghetti, T, topology model. Let's understand this. Unlike spaghetti model, topological model explicitly build relationships. Topology is the term used to describe the marking of spatial relationships. In fact, topology adds intelligence to the database in a geospatial environment by explicitly building linkages and evolving relationships. Topology is one of the most useful relationships maintained in many spatial databases. It is defined as the mathematics of connectivity or adjacency of points or lines that determine spatial relationships in a GIS. So in case if I ask you which model is the one which is one of the best ones, it's topology. It understands the connectivity, it understands adjacency, it understands relationships, it understands spatial relationships. That is so very important for spatial analysis. And GIS is what? GIS is spatial information system that talks about analysis by which we can retrieve data anytime, we can predict data, we can simulate a lot of information, and we can build and solve many puzzles, and we can also pick up a scenario which can happen in the future. So that for that what we need is a topological model. Topological data structure logically determines exactly how and where points and lines connect on a map by means of nodes, topological junctions. Burrow calls them, and we also call that now. Tell me, so what are the nodes called? Topological junctions. What you are reminded of your train junctions? Same, it's a junction only where the lines are getting connected. In the process of topology building, relationship points, lines, and areas are calculated and encoded. Topological data define the logical connections between points, lines, and area for geographical description and analysis. Connections between spatial objects, for example, information on areas which bound a line segment are considered to be topological data. From this, adjacent spatial objects may also be identified. The topology of any line would thus include the starting node, its destination node, and the left and right polygons through which the line passes. and the figure talks about topological model and topological warp model. The topological structure permits, as shown in the figure, encoding of the geometry of the data with no redundancy. The report, in case you look at it, it notes that the geometry of the data is encoded with little or no redundancy in arc node structure, and the database can also include attribute data for each node. And these are expanded in the attribute table, which explicitly links it to the geometry of the spatial object. So, in case if we look at the three these structures, one is connectivity. Arcs connect to each other at nodes and provide information about linkages among spatial features. An arc node topology was developed several decades ago as a convenient way to store information of this sort. It is used to encode information, which is also used in the census data, the boundary files, and people have been using it. A lot of software companies are also using it, and ArcGIS and all other solutions are also using it. Area definition is also there that connect to the surrounding area, defining a polygon. Polygons are defined by a series of XY coordinates that connect to enclose the areas. GeoMedia and all others are using this. But ArcInfo shows the arcs defining the polygon. And a list of arcs that make up each polygon is stored and used to construct the polygon as and when required. The third one is contiguity. Arcs have direction and left and right polygons. So, every arc has direction from node and to node. This direction has been maintained in the list of polygons as on the left and right sides of each arc. Thus, any polygon sharing a common arc are adjacent. This direction has been maintained in the list of polygons. And the 5 axioms which we have to remember in the topology are as follows. Thus, all arc ends in the points of the nodes. Arcs cannot intersect except their nodes. Areas are completely enclosed by arcs. Areas do not overlap, and every location is written with some area. So, that is something which is so very important in case if we have a look at it. Just now we talked about the 5 axioms, let us just revisit them. Number 1, all arcs end in points or nodes. Arcs cannot intersect except at their nodes. Areas are completely enclosed by arcs. Areas do not overlap, and every location is within the same area. This is something which is so very important. So, now let us understand the planar topology. All features in planar topology occur in a 2-dimensional surface, and there can be no overlap among lines or polygons in the same layer. These lines are non-planar because all lie in the same plane, and therefore line crosses over an underlined segment. I hope you are understanding this. The lines would intersect at node. Similarly, in the case of polygons in planar surface, if and when overlap, they need to be resolved as placed one above the other with nodes located at the intersection of the boundaries. If we look closely at the figure, we will find the presence of 3 polygons, isn't it? Yes. So, now that is something which for us to understand. In other words, what we can say that topology defines connections between features, identifies adjacent polygons, and can define one feature such as an area as a set of lines. It is so important. And the rule of the thumb for topological data structure is that anything of intersect on a map must be explicitly defined as point, line or area in order for systems to perform any sort of spatial analysis on the data. I think this is clear. The geometric characteristic of spatial entity may be described in terms of its 2-dimensional shape, its distance between like or different entities, how it is connected to other entities, and what entities occupy the space adjacent to it. And such characteristics may be easily described either in words or by a system of coordinate grids on a map. Spatial entities can be described in terms of their dimensional characteristics. If these entities were to be changed by some kind of transformation, all the characteristics of these spatial entities would likewise change. Shape can be made smaller lines, made longer, and so on. In other words, there is a fundamentally change to the entity itself. So, before we end this chapter, let us also just spend 1 minute on what is mathematical topology. Mathematical topology is a branch of mathematics based on graph theory, which deals with geometric properties and remains unchanged under certain transformations such as bending or stretching. The characteristic of this model is that it explicitly records adjacency information among spatial entities with point lines and polygons. Mathematical topology assumes the geographic features occur on a two-dimensional plane. Through planar enforcement, a spatial feature can be represented through nodes, zero-dimensional cells, edges, sometimes called arcs, one-dimensional cells, or polygons, two-dimensional cells. So this is what it is. So isn't it like, in case if you want any help, my friends, all of you, when you start working, pick up a friend from mathematics department and learn more. The order of connectivity defines the shape of an arc or polygon. And the computer stores this information in various tables of the database structure. And by storing information in logical and ordered relationship, missing information also can be revisited. What does GIS do? GIS manipulates, analyzes, and uses topological data in determining data relationships. And that is what is the strength of GIS. We can also examine spatial relationships based upon locations, as well as functional and logical relationships among geographical features. Isn't that something what we all wanted all this while? In case if somebody asks you what is the difference between CAD and GIS, that's what it is. CAD doesn't allow analysis, which GIS do. So what have we learned today? We have learned largely three things. Number one, data compaction or compression is common in GIS and is based on different algorithms that reduce the size of computer file but maintains all the information intact. And there are generally two types of compressions algorithms, where one may be lossless, where no information is lost, and the second may be lossy, where some information is lost. And then we also learned today that there are 4 types of data compression techniques in raster GIS. Which are those? Remember, chain coding, yes, run length coding, very good, block coding, wonderful, and quadtree. And we all can know about them. And the vector data model, if you remember, they are the ones in case we learned today 2 techniques. Which are these 2 techniques? Yes, S, spaghetti model, and then we also learned topological model. Agree it was theoretical, but my dear friends, when you start using, it is so very important for all of you to know this, because then only you can play with it. Why do you enjoy fun games, dear friends? You enjoy those fun games in the digital mode, or the kids know because you understand how the data is stored, and that's something so very important. So just remember that. Do not get worried that it's too much maths. It's only somewhere the software company who has evolved the software which you're using are already embedded this into your system, but your job is to just know about that, use GIS as a tool for big time analysis. It was fun today sharing this lecture with you, and I hope you all enjoyed it. I enjoyed it at least. Please use GIS for all your spatial decision making. Thank you very much.